All right, welcome everyone. If you're gearing up for your VTU machine learning exam, you've landed in exactly the right place. Consider this explainer your ultimate go-to exam cracker. Today, we're diving deep into Module 4. Specifically, we're mastering the ins and outs of reinforcement learning, plus the absolute essentials of pack learning. We're going to break down the exact definitions, the mathematical models, and the algorithms you actually need to know. By the end of this, you'll be able to confidently tackle both the theory and the numerical questions they throw at you. Let's get into it.
Okay, so here is our roadmap for the explainer. We'll start with 1, an intro to reinforcement learning, then 2, comparing machine learning paradigms, 3, the core components of RL, 4, Markov decision processes, 5, returns and rewards math, and finally 6, Q-learning and pack basics.
Section 1, Intro to Reinforcement Learning, Navigating Uncertainty. So at its very core, reinforcement learning, or RL, is kind of like mimicking human behavior, right? We observe our environment, we process what's happening, and we take trial and error actions. It's an absolutely perfect setup for environments where there's a lot of uncertainty. But unlike working with a nice, neat, simple data set, RL agents face some seriously tough challenges. And hey, these actually make for fantastic short answer questions on your exam, so pay attention. First off, designing the right reward and its value, extremely difficult. Second, a lot of real-world problems just don't have a fixed model or fixed rules to follow. Third, we're constantly dealing with partial observability. Think of it like trying to predict the weather when you can't even see half the variables. Fourth, exploring massive complex state spaces takes a ton of time. Agents are constantly stuck in this dilemma of exploration versus exploitation, meaning, do they explore new, unknown actions, or do they exploit the ones they already know give them rewards? Just picture a self-driving car or an AI playing the board game Go. The sheer number of possible actions makes traditional labeled data literally impossible to use.
Moving on to Section 2, Comparing Machine Learning Paradigms, where RL fits.
Now, there is a really stark contrast between RL and supervised learning. In supervised learning, you've got a supervisor. You have labeled data right from the jump, and your feedback is usually pretty instantaneous. But in reinforcement learning, there is absolutely no supervisor and 0 labeled datasets initially, none. The decisions the agent makes are dependent on one another, and they're made sequentially. And unlike classifiers that have predefined target classes, RL doesn't have initial target values. It is purely goal-oriented, and it relies on feedback from the environment that is very often delayed by time.
So then, how does it compare to unsupervised learning? Well, while both of them lack those predefined target classes, there is a massive difference in how they interact. Unsupervised learning has no mapping from input to output, and it gets 0 feedback from the environment. Reinforcement learning, on the other hand, does map inputs to outputs, and it absolutely relies on constant, ongoing feedback from the environment so it can actually improve its policy.
All right, Section 3, Core Components of RL. The feedback loop. Every single RL problem out there relies on this one continuous cycle. You have the agent, that's the autonomous body, like a robot or a piece of software, that looks at the world and makes a decision. Then you have the environment, which is the world where all these actions actually take place. When the agent takes an action, the environment updates itself and spits back a new state and a reward. It's a continuous loop. Now, the strategy the agent uses to actually pick these actions, that's called its policy. And the expected long-term return of being in a certain state is called its value function. Ultimately, the goal here is always to maximize total rewards through this continuous cycle. As the agent navigates through this environment, it generates a sequence of states, actions, and rewards from start to finish. We call this entire sequence an episode. For the exam, you need to know the 2 main types of tasks here. Episodic tasks have a well-defined start and a really clear terminal, or goal state. Think of a game of chess, right? It eventually ends in checkmate. Continuous tasks, on the flip side, have no designated goal state. They just keep going and going like an ongoing algorithm for stock trading, or a robot just continuously trying to maintain its balance. Okay, Section 4, Markov decision processes, the mathematical framework. To actually solve these reinforcement problems, we usually formulate them mathematically as a Markov decision process, or MDP. But here's the kicker. An MDP is built on one very specific, absolutely fundamental rule. So the crucial point you must remember is the Markov property itself. This property states that the future state depends only on the present state, not on the past history. Let me say that again. It only depends on the present state. If you know exactly where you are right now, How you got there doesn't matter at all for predicting where you can go next. Let's picture a classic exam scenario, a Markov chain with two states representing two universities. Students are transitioning between University A and University B based on some specific probabilities. Looking at this setup, 80% of the students in University A leave for B, while 20% stay right there in A. Meanwhile, over at University B, 60% of those students move to A and 40% stay put in B. These pathways, or edges, represent the transitions between the states. To solve this mathematically, we take those exact transition probabilities and convert them into a matrix, which we denote as P. Notice how the top row represents University A, 0.2 staying, 0.8 leaving. The bottom row is University B, 0.4 moving to A, 0.6 staying. Now write this down. A key rule to remember for your exam is that the sum of the probabilities in each row of this transition matrix must always equal exactly 1.
Now, on the test, you'll likely be asked to calculate a future state based on this matrix. If we know the initial distribution of students, let's say 28% in University A and 72% in University B, we can predict year 2. How? By simply multiplying that initial state vector by our transition matrix P. You literally just multiply the row by the column to get your new values. This is practically a guaranteed way to score points on your exam. Just set up the matrix, double-check that your rows sum to 1, and perform that basic matrix multiplication to find your new state probability. Easy points.
Next up, Section 5, Returns and Rewards Math, Valuing the Future.
When we talk about an immediate or undiscounted reward, you literally just add up the rewards from every step. Simple enough, right? 10 plus 20 plus 30 plus 40 equals 100. But here's the thing. In RL, we usually care a lot more about immediate rewards than we do about distant ones. Why? Because the future is uncertain. So we use a long-term discounted reward formula. This involves multiplying future rewards by a discount factor called gamma, which is usually set somewhere between 0.8 and 0.9. By raising gamma to a higher power for each subsequent step into the future, the mathematical value of those future rewards shrinks. This brilliantly helps the agent prioritize what is right in front of it.
All right, bringing it home with Section 6, Q Learning and PAC Basics, Algorithms in Action.
First things first, you absolutely must distinguish between model-based and model-free learning. Model-based learning is passive. It assumes you have a known environment, meaning all those probability distributions we just looked at in the Markov matrix, they're already known. It uses dynamic programming to solve the problem by reusing stored solutions. Model-free learning, however, is a different beast. It does not assume any prior model. The agent has to learn directly from interacting with the environment through good old trial and error, using methods like Monte Carlo or temporal difference learning to update its knowledge purely based on its own experience.
So, let's see how this all builds into the famous Q learning algorithm. Basically, the agent builds a Q table to track the value of its actions. After it acts and gets reward, it updates the Q value for that action. For the exam, you've got to remember the core logic of this update equation. It takes the old value and it adds a portion of the learned value, which is just the immediate reward plus the discounted maximum future reward. This blending of old and new information is controlled by your learning rate, alpha, and your discount factor, gamma. To quickly wrap up the syllabus, let's look at the computational learning theory side of things, specifically PAC learning. That stands for Probably Approximately Correct. It was introduced by Leslie Valiant back in 1984. The entire goal here is proving that an algorithm's error on new, unseen data is small, say, less than or equal to 5%. You should memorize this exact setup. You have an instance space X, a set of Boolean target concept C, a distribution D, and a learner L with a hypothesis space H. You'll use this framework to calculate sample complexity, which is just the number of examples you need to guarantee this low error. Or you'll use the mistake-bound model to track exactly how many errors the learner is going to make before it finally converges. Okay, I'm going to leave you with this provocative thought to tie everything together. We learned today that the Markov property strictly assumes the future depends only on the present state, right? But earlier on, we also established that one of the single biggest challenges in real-world RL is partial observability, situations where the agent cannot fully see its present state. So, if you can't fully see the present, how on earth can your MDP accurately predict the future? That exact tension is where the cutting edge of machine learning research sits today. It's a huge open problem. Study hard, master these fundamental concepts, and best of luck crushing your Module 4 exam. You've got this.